Alright, so in the last couple of videos we took a look at a system with two normal modes, so two masses on a collection of three springs. And we can extend this to a system with n such modes. So let's go ahead and see how that looks. So the kinetic energy we can write as 1/2, and here I'm going to use generalized coordinates, so we'll say q dot twiddle. So this will be a generalized mass matrix. Q dot without a twiddle. And it'll be convenient in one step especially to use index notation. So we can write this as 1/2 sum over jk, both running up to n of m jk qj dot qk dot. All right. Without any loss of anything, we can let make all of our generalized coordinates be 0 at equilibrium. And so with that choice and suitable clever choices to make the potential 0 at 0, we can write the potential energy as 1/2 q twiddle times our coupling matrix times q. And again, in index notation, that would be 1/2 sum over j and k, running up to n of k jk qj qk. All right. So we can write our Lagrangian then. That'll be t minus v. So that will be 1/2 q dot twiddle m q dot minus 1/2 q twiddle k q. Or we can write that in index notation as 1/2 times the sum over j and k mjk q j dot q k dot minus k jk q j q k. All right. So then we can attack all of our equations of motion all at once with this summation notation here. So we can write our equations of motion as partial L partial qk minus d dt of partial L partial qk dot. All right, and that's got to be equal to 0. All right, so if we go ahead and differentiate away, we've got, okay, differentiate by qk, that goes, so I have minus 1/2 kjk qj, so that's sum over j, right? Minus from here, differentiating that gets rid of that. And then differentiate with respect to time makes dot double dot, so minus 1/2, again sum over j, m jk qj dot. All right. Well, I can certainly, and that's going to equal 0. So I can certainly times through by -2, then make it a little prettier. So this becomes sum of m jk qj dot, double dot, I mean, plus k jk qj equals 0, letting our k run from 1 to n, our total degrees of freedom. We're going back into matrix notation. We can write that as m operating on our q double dot plus k operating on q equals 0. All right. Well, we know how to go ahead and do this. So just like before, you'll try a solution. We'll let the q, or vector q equal sum a times the cosine of omega t. All right, so we can plug that in. When I differentiate this twice to go into here, I'm going to get a minus omega squared coming out front. So minus omega squared times m operating on a. I have a cosine omega t. And then just substitute into there plus k a cosine omega t equals 0. I can certainly divide through by cosine omega t to make that go away. So if I rearrange that a bit, that becomes k minus omega squared times m times a equals 0. We go, wait a minute, that's an eigenvector equation. So, or secular equation. So sure enough, our secular determinant then will become that the determinant of k minus omega squared m equals 0. Now, at this point, you say, well, hey, we've done this all before, or I'm just going to be solving a nastier polynomial. So let me just show you a quick cautionary tale about that. So I went ahead and set up such a system here. So here's a nice 3x3 system with some weak coupling off to the side. And sure enough, it finds all of my eigenvalues. And then I ask it for the eigenvectors, and there they are. Okay, here it's being quoted as a span because these are degenerate eigenvalues. But you just go ahead and pick out something perpendicular in there. All right, so then we take it up to 4x4. Okay, that looks good. I ask it to solve it, and it pops out all 4 of my eigenvalues. Ooh, this is sounding good. And sure enough, here are all 4 of my eigenvectors. Oh, this is great. All right, drunk with power, let's go ahead and take this up to a 10x10. There it is right there. And we solve it, and Mathematica pukes on me. This root thing here is saying, hey boss, I don't know how to solve it. There's a really good reason for that. I could have just made this 5x5 and I would have had exactly the same problem. And that's because there is no general formula for getting the roots of omega squared when our degree in omega squared is 5 or greater. There just isn't. You can do some stuff by using infinite series or hypergeometric functions. But in general, you can't just blithely solve for the eigenvalues and then go crank out the eigenvectors, which is really unfortunate. But remember, if you know how to describe the symmetry of the situation, you can always set the problem up in the normal modes directly and go from there. So since we're heading to trying to handle a system of every single molecule on the string, we're certainly going to have to figure out how to be more clever. All right. So with that cautionary tale out of the way, somehow we get our eigenvectors. And they are qk of t is equal to our ak times cosine omega k t minus delta k, just like before. So we're running again. Excuse me. K equals 1 to n, and our AKs are column vectors of A1k, A2k, and so forth all the way down. All right. So we can certainly go ahead and work in a Q space with a diagonalized Lagrangian. We transform back and forth by, say, our generalized coordinates are equal to our transformation matrix A times Q, and back by doing Q equals A inverse times Q, and A inverse is easy to get because it's a twiddle. All right, now as before, we can say that our A matrix is equal to a row matrix of the column matrices A1, A2, A3, and so forth. All right. So with that, our next video is going to be taking a look at the vibration of a loaded string. So we're going to go ahead and ramp it up to n masses.